I will be talking about the joint work that I did with my two colleagues, Noah Shati and Oscar Higet. And it is about Tesseract, which is a search based decoder for quantum error correction. So, first of all, probably a lot of you are familiar with pi matching, which runs a Blossom algorithm over the Tanner graph. On the right side of the screen here, you can see the Blossom algorithm is running on the slow match. The visualization is from Craig Gidney. And the only difference is that it's not running on a disk like this. The pi matching is running the Blossom algorithm on the Tanner graph that you're seeing on the other side of the screen here. The edges here are the errors, and the vertices are showing the detection events or detectors in some sense. Um, and this algorithm does a really, really good job when we don't have hyperedges, or at least we don't have undecomposable hyperedges. But when your Tanner graph has complicated hyperedges, this algorithm, or basically Blossom algorithm, is not able to do a very good job at decoding. And the whole purpose of Tesseract is to give the same capability to the researchers or whoever wants to do decoding, um, to be able to do that for the graphs that have complicated hyperedges. For example, here you see a Tanner graph for a distance 9 color code, and you see not only it's very dense, it has all those hyperedges, and on the other side you see the Tesseract decoder that is able to decode over this complicated Tanner graph. We, in this visualization form that you're seeing here, the red edges or hyperedges are showing the errors that are active at that moment, and the blue ones are basically uh, the detectors on that slice of decoding process that we are doing, and it's pretty fast. And it's designed to be fast or high performance uh, as a decoder. And because of that, we wrote it in C++. But now, thanks to our colleague Noor Yusri at Google, also there is a wrapper around the C++ implementation of Tesseract, which allows the researchers to use it in Python code. And it is as easy as just doing pip install Tesseract decoder and call the decoder inside your Python code. So inside this talk, this is the outline. First, I'll give you a few motivating examples that why we care about this most likely error decoder, such as Tesseract. Next, I'll move on to what is Tesseract and how it exactly works, how you can use some heuristic to tune the performance of Tesseract to run even faster, and finally, how you can use Tesseract to do protocol comparison and make better research decisions based on the results you can get from the Tesseract decoder. So, first of all, let's try to look at some of the examples of why we care about this most likely error decoding algorithms or MLA decoding algorithms. Um, the first example is about this work from Maddie Kane and her colleagues at Lookin's group when they were working on transversal gates for neutral atom arrays. In the beginning, they needed a most likely error decoder to validate the idea and see if it's actually fault tolerant. And for that purpose, they used the most likely error decoder, which was an integer programming decoder, to validate the idea. And later on, after this validation, they worked on to come up with fast correlated decodings for their transversal algorithm. But at first, it was an MLA decoder that gave this capability. The next two examples that I'm going to show you are from the works that we did at Google. So this is one of the later. This plot here is basically from one of the latest paper from Google that compares the performance of color code versus surface code, which the blue line shows surface code and the yellow slash orange colors are showing the logical error rate for color code. And you can see uh, in two examples for error rate of 0.005 around distance 5 or 7, color code surpass surface code. And same for error of 0.001 around distance 9, color code surpass surface code. And this is an amazing finding because it shows that in very realistic distance and very realistic error rates, color code can show better logical error rate compared to surface code. Um, and it is, we were able to do this by using MLE decoders. Another example is the magic state cultivation. But the current version of magic state cultivation doesn't have, of course, it doesn't have MLA decoding. But to give you a little bit of backstory, in the early stages of the cultivation, there was this idea that a smaller, they wanted to expand a smaller color code to a larger color code, which contains the same logical magic state. But to do this expansion and validating the idea, there was a need for an MLE decoder to check if it gives the confidence that is needed. And again, after that, it moved to the expansion to the with the surface code. But again, an MLE decoder was needed in the beginning to move further with the idea. So, with all these examples, I wanted to show that MLA decoders are useful to give you an upper bound of how well how far you can go, and also de-risk the protocol choices that you need to make inside a QEC research problem that uh, you are facing. Now let's get into some of the examples and some of the things that Tesseract is able to deliver. But before getting into the details, I wanted to show you some of the results that have been possible because of Tesseract. Since Tesseract is almost general, we are able to use it for decoding different protocols. Here I'm showing 4 different protocols starting from surface code, super dense color code, surface code, bicycle codes, and transversal CNOT. The top charts are showing the logical error rate, and the bottom chart are showing the decoding time. But the two interesting examples here are for color code and bicycle code. We can see that with Tesseract, we are able to improve the logical error rate up to 100 times or 2 orders of magnitude in when we are comparing to other state-of-the-art decoders. So here, for example, in color code, we're comparing with Chromobius, and you see the 100 times improvement. And Tesseract is able to do as good as the integer programming decoder, which is pretty accurate. But obviously, we are paying in terms of execution time, but still, Tesseract is about 10 times faster than the integer program decoder. Same behavior we can see here with bicycle code that we are comparing with BPUSD, and Tesseract is about 100 times better than BPUSD. Although the gap between Tesseract and BPUSD in the time is not as big as what we saw there. So here, again, as a motivating example, we can reduce the logical error rate by orders of magnitude. Now, how does exactly uh, Tesseract work? Tesseract does a search over a graph, which is not the Tanner graph. It is the graph of all the subset of errors. It starts with the empty set, And by each edge, it's adding one error to the previous set that it has. And the weight of each edge is basically the cost that added error is adding to the total cost so far. We have an early exit condition, which basically checks if that subset of error is able to explain the syndrome data. And that is basically our answer. And if you are able to introduce a search algorithm, which here is Dijkstra with a combination of A star, you basically can solve the decoding problem here. But I wanted to explain the idea in the sense of with an visual example. Here, let's assume we are looking at our error model or Tanner graph in terms of these detectors in the circle pattern, and we have errors in this hyper edge pattern that we are showing with this mm, triangles. Um, and let's go over an example. Let's assume this is a portion of a color code Tanner graph. And what we are seeing in our syndrome data is these three detection events. Um, so now the problem that Tesseract decoder should be solving is what are the subset of errors that could explain this set of detection events? And that as the first step, Tesseract decoder gives a series of priorities to these detection events. It could be random, but there are a lot of different techniques. But let's assume that you have this priority list and start with the top priority of the detection events. Now, when Tesseract wants to explain these detection events, it has three options of A, B, C for the error that is associated with the detection events. And we know that if it makes the choice A, now there are two remaining detection events that it needs to explain in the further steps. If it makes the choice B, there are no remaining detection events to explain. And for the choice C, there are still two remaining detection events. Bear in mind that at this stage, the algorithm is not done yet, so it wouldn't disregard any solution. It keeps track of all the solutions, but it also keeps track of a series of metadata that helps make smart decision along the way. For example, in this case, we know that for A and C, if it keeps these cases, there are at least two detection events. And for these two detection events, there are at least two more errors that must be activated to explain these detection events. And the reason is that there is no one error that is connected to both of these two remaining detection events. So there's a need for two errors at least. But for the case B, there is no remaining detection events. And we are keeping track of this metadata inside a priority queue. And basically, we are keeping the cases of whatever cost has been considered so far, plus a lower bound of the remaining cost for the remaining detection events, which is the blue cost that you are seeing here for each of those path or decisions that the decoder is making here. So now let's go further and see how Tesseract uses this information. So we have all these costs inside our priority queue, and it is each of these solutions associated with that cost. But what the search algorithm does is tries to choose the one that has the lowest cost and pops that out of the queue, which is here the one with the cost one. But also we are applying this exit condition, and in this case, we are satisfying the exit condition because this specific case, a simplified case, allows an explanation for the whole syndrome data, and basically it's done here. So Tesseract will returns that answer. But if it wasn't done here, it will just continue the search until it meets the exit condition. But one very important aspect here is this extra metadata, which is a lower bound on what is the remaining cost of that the decoder needs to explain. before uh, solving the whole problem of decoding here. We here we use the dead cost for how we are defining this lower bound. Um, in the paper and in our GitHub page, still this is the name that we are using for it. If you wanted to understand exactly what's happening there, but this is just a simplified version that I explained here. We have it with more details inside the paper. But one good catch about this dead cost is we can use this metadata to guide our A star search, which makes the algorithm very fast in practice. So now that we know about how, in some sense, how the algorithm works and how allows us to get to the most likely error that is consistent with our syndrome data, we wanted to take it some step further and make it run even faster in practice. But some of these steps, they can make it heuristically not as accurate as the general case. But let's look at these ideas. We applied a series of optimizations uh, into the search. The first one was we are pruning the graph um, in different layers based on the observation we've done so far. Another optimization that we deployed and helped a lot with the performance is the A star search, which uses the dead cost as the heuristic. We also realized that the reordering of detection events can help with the performance. So we have an ensemble reordering. Another good technique that's used in search algorithm is beam search. We apply that. And we also have a beam climbing, which means we increase the beam as we go deeper. The other two improvements are we are trying to not revisit the detection events we've already seen or assign some penalty if we are increasing the number of detection events. And all of this help Tesseract to be very fast in practice. Now let's look at some of the cases that Tesseract is able to do a really good job and how these heuristics can help. So here we have a distance 5 color code. You can see there are cases that there are hyper edges with 3 detectors. And when we run Tesseract on this distance 15 color code with error of 0.05, um, it without introducing any beam there, you can see that it's kind of taking a little bit long to get to the answer. But with applying the beam search in the next example, which does a cutoff of 5, the algorithm gets to the answer pretty fast. And it doesn't do any extra work there while getting to the final answer. Here there we have another example, which is the gross code. You can see the Canada graph is pretty dense. There are hyper edges with 9 detectors, which shows how challenging a decoding solution could be for this example. Um, and this is an example of that bicycle code with the same visualization. You saw how dense it was. And when we wanted to run decoding with Tesseract for that gross code with the level noise of 0.002 and a beam cutoff of 10, you can see that Tesseract is progressing pretty fast and got the answer, even though it was pretty dense. We have the answer pretty fast. Another example here, you can see a super dense color code. Again, a lot of hyper edges. Um, and just for comparison, you can see here there's a nice and friendly surface code with detectors up to 4. But when you just look at the graph like errors, which are like 1 or 2 detectors, and you can decompose to it, it's um, still pretty nice. But when you move to the color code in this example, you see that there's a lot of those hyper edges with many detectors, up to 6 detectors. Even for the case of a small and spiky middle color code, we see up to 6 detectors, hyper edges. And for these examples, still Tesseract is able to do the decoding pretty efficiently. Here I'm showing an example for distance 11 with beam cutoff 5, and you saw that it just finished it in a few seconds. Another promise or another use case that you can use Tesseract for is to make comparisons between different protocols or de-risk the decisions that you're making on your protocols. Um, for example, when we wanted to compare surface code with bicycle bivariate code, and you're using fast decoders such as sparse blossom or BPOSD, uh, for the case of if all the couplers are equally noisy, we can see on these two cases, which is the surface code and this color code, you will get 10 times improvement in the number of the qubits that you have. And if you make the assumption that long range couplers are like 10 times noisier, which is this NLR 10, still you get like 2 times improvement here, which is these 2 points. So you with these decoders, you can make some assumptions on which protocols could give you better qubit counts. But uh, you see these comparison are some good conclusion from the decoders. But when you use a more accurate decoder like Tesseract, you can say that you can do better comparison between these different protocols. For example, in this case, when all the couplers are equally noisy, you see a 20 times improvement. And for long range couplers being 10 times noisier, you see 3 times improvement. And this kind of gives a new way of looking at the problem, that you can only focus on the protocol and isolate the impact of the decoders, which is again could be helpful in the decisions that you're making on your protocols. Another example is from this plot that we got from the paper from Craig Gibney and Cody Jones on the new circuits. And there, in this paper, the Chromobius decoder is introduced, and one of the conclusions was that middle out color code is doing a better job compared to the super dense color code. And later on, Noah made this plot using an integer programmer decoder using High's library, which is a C++ fast decoder. But here, now you see a different conclusion, that super dense color code is doing better than the middle out color code. But for getting this plot, he had to run this experiment for a few days and use a lot of compute power. However, now with Tesseract, you can do a comparison with super dense color code and middle out color code with very small margins, but only on a laptop with a few hours of simulations, which wasn't very possible with previous examples that you saw here running for a few days. This is another nice example for from the Sasha and his co-workers on an anonymous fault tolerant protocol of 50 data qubits on unpublished data. And you can see, comparing to Tesseract with BPUSD, they were able to improve their logical error rate 2 times, which is interesting. We also compared Tesseract with the other decision tree decoder and MaxSat and another integer program decoder. And as you can see, for the color code of distance 9 and 13, both of the cases, Tesseract is doing a lot faster compared to those. And if so far you got interested on Tesseract and you wanted to try it out yourself, here we have a good Python notebook that you can try a few examples and try to play with different heuristics to get better performance for your own case. Um, Feel free to check that out. And by that, thank you so much. If you have any question, please feel free to email me or my colleagues Noah and Oscar, or open an issue in our GitHub page. Thank you so much.